In this particular video, we're going to look at the notion of cardinality of sets. And the thing that I want to kind of point out is that cardinality of sets is really a way of talking about the size of sets. And so I kind of want to start with an informal notion. One way about thinking about the size of at least a finite set is to be thinking about it as the number of elements inside the set. So if my set was something like a is equal to 17 comma pi, and then, I don't know, the square root of 3 over something weird like e squared plus 17, I can think about this set as having 1, 2, 3 elements. So I want to kind of make that note. A has 3 elements, and I want some notation for this particular fact. And since I'm thinking in terms of this number of elements is somehow like the size of this finite set, I'm going to reuse notation that indicates size inside of the set of real numbers. In other words, I'm going to use what looks like absolute value notation. And so we're going to write that the size of this set is equal to 3, meaning that we have 3 elements. So very informally, this is the size of A is 3 elements. But we usually don't read it that way because this is not going to extend when we have infinite size sets. So the more formal notation, the formal way of reading this is to say the cardinality of A is equal to 3. So in the finite world, the cardinality of a set is just the number of elements inside the set A when A is a finite set. That does not work very well with infinite sets, and we'll look at that in just a few minutes. But I do want to think about what it means to say 2 finite sets have the same cardinality. So I want to kind of look at this idea. If I say that the cardinality of A is equal to the cardinality of B, and A and B are both finite, that means that I have the number of elements in A is equal to the number of elements inside set B. And if they have exactly the same number of elements, then it's easy to make a one-to-one correspondence between the two sets. And that's what I kind of want to collect next. So if we have A and B have the same cardinality, and again, right now they are finite sets, what that tells me is that if I happen to be able to write A as A1, A2, all the way down to AN, so the cardinality of A is exactly equal to N, then B had better be able to be written as B1, B2, all the way down to Bn. And what I want to notice is that we get an obvious correspondence, a one-to-one correspondence between the two sets, given by those red arrows. In other words, what we've got in this situation is the fact that we can easily find a function that goes from A to B that is both one-to-one and onto. In other words, F is a bijection, or in high school language, F is a one-to-one correspondence. These phases, one-to-one and onto, one-to-one correspondence, and bijection all mean exactly the same thing, and it's just a matter of what kind of setting you're in to pick the vocabulary. Like I said, this is typically used in high school. This is used in upper division math classes, and both of them mean this. So that's basically the definition of these two ideas. Well, we can extend this notion that two sets have the same cardinality. We can extend this notion that two sets have the same cardinality if we have a one-to-one and onto function to any kinds of sets, including infinite sets. And so that's what I want to look at next, is the more formal notion of cardinality. So the formal idea of cardinality actually is something that is defined on pairs of sets, and at this point we no longer need A and B to be finite sets. A and B can be any kind of sets. So if A and B are sets, they may be finite sets, they may be infinite sets, it does not matter. We are going to say that A and B have the same cardinality, that the cardinality of A is equal to the cardinality of B, if and only if we can find a function that goes from A to B that is both one-to-one and onto. In other words, we can find a bijection between the two sets. Now, the advantage of this bijection idea is that it lets us talk about when two infinite size sets have, in essence, the same size. And I kind of want to look at that briefly in this particular video. We'll explore it in much more detail in a few other videos. So what I want to do is I want to think in terms of this. Let's look at the set of integers and the set of natural numbers. It turns out that it is very easy to show that these two sets have the same cardinality. And here is one basic way of doing it. I can list the elements of z as follows. I can start at 0, and then I'll go 1 and -1, and then I'll go 2 and -2, and 3 and -3, and 4 and -4, and 5 and -5, and so on. And I basically want to observe that for every integer, every k inside z is somewhere on this list. And it's just as important to realize it's on that list only one time. Well, now what I want to do is I want to actually list the elements of the natural numbers. The natural numbers are the counting numbers. They start at 1, so they go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. And the bijection between these two sets is staring us in the face. These white arrows are going to be a bijection between the two sets. Now, I've not done a formal proof here, but this is something that should convince you that, yeah, there is a bijection. Those white arrows are a bijection between z and n. And that's enough to say that the cardinality of z is equal to the cardinality of n. Now, it turns out that infinite sets that have cardinality equal to n are pretty important in many areas of mathematics, and they behave very differently than infinite sets that do not have the same cardinality as the natural numbers do. And that gives rise to the following definition. So let's let A be an infinite set. If it turns out that the cardinality of A is equal to the cardinality of the natural numbers, we call A countable set. And the importance about this is that if A is countable, then we can actually list the elements of A. So we can list the elements of A. In other words, we can say that A is actually equal to A1, A2, A3, A4, A5, and the list goes on forever. And of course, once I have that, if you think about it, I can easily put in down here 1, 2, 3, 4, 5, and so on. And there is the bijection between A and the natural numbers. So it's really important to realize that any countable set can be listed. But just as important, if we have a set that can be listed, so if I've got a set, I'm going to call it B. If I've got a set B where I can list it, but the list never ends, then I can easily put that set into one-to-one correspondence with the natural numbers. And the bijection looks like this, of course. So if I can list, then I can say that the cardinality of the set that I listed is the same as the cardinality of the natural numbers. And so that brings into play an important theorem that, while we've not proved it formally, we've got the insight into why it works, and I do want you to be aware of this theorem. And this theorem basically is going to say that if I have an infinite set, then the cardinality of A is equal to the cardinality of the natural numbers if and only if A can be listed in the way that we just did. In the next couple of videos, we're going to have you look at showing that the cardinality of the rational numbers is actually equal to the cardinality of n, but the cardinality of the real numbers is not equal to the cardinality of n. And because of this fact, we say that the real numbers are uncountable. And sets that are uncountable cannot be listed. So you'll explore that in the next two videos.